as you can see, I kind of borrowed the title from a famous book in signal processing. And well, this is joint work with a wonderful group of people, including my advisor, Michael Wakin. And as you can see, Holman still lives in 1920s without color photography. But anyway, so I'm going to talk about manifold models. So high-dimensional data, even though very often has a very simple structure to it, and might live on a low-dimensional manifold or surface, whichever you want to imagine. So I will give a few examples, but as just one example, each pose and location of that cube on the left would correspond to a point on the surface, on a very low-dimensional surface on the right, whereas each photo itself could have hundreds of pixels. Well, to answer questions about data, we need to take measurements. So imagine this measurement operator phi that maps Rn, the space of our signal or data, to Rm, and m, number of measurements, is typically much smaller than n. So it's very natural to ask, what is a good measurement operator? Well, a good measurement operator would, in a sense, preserve the geometry of the original surface M. So phi of M, image of the surface under this measurement map phi, will look very much similar to the original one, in the sense that the pairwise distances between points on the original surface are nearly preserved in the image space. So I cannot show it with this expression for every pair of points on the manifold. So, well, it's very natural to ask that, well, do we even have a good measurement operator? Does it exist one for a given surface, given manifold? And actually, before that, I should say that if we do have a good measurement operator, then we can answer a lot of questions about data by just looking at these measurements, because in a sense not much information was lost when we came from Rn to Rm. Well, the answer is that, as a matter of fact, they are very easy to construct, and there are plenty of them out there. So let's just imagine that phi, the measurement operator, is a generic linear operator from Rn to Rm. And by that, I mean that we can represent it with a m by n matrix, and it's random. So it could be, the integers of it could be just random Gaussian variables. Then, if the number of measurements m is large enough, we indeed, with very high probability on the choice of phi, we do get an operator that's excellent, in the sense that, yeah, it preserves pairwise distances from on the original manifold. So let's look at this number of necessary measurements. There are a few parameters involved. One of them is dimension of the surface, volume of the surface, and its reach, which is a measure for the overall curvature of that surface. And you can tell that, well, first of all, number of measurements that you need is, in a sense, linear almost with the dimension of that surface, which is very nice. Or this is, in a sense, number of rows of that matrix that you would need. And also, the larger the volume or the smaller the reach, you would need more measurements. So let me quickly talk about reach. I'm not going to formally define it, but the surface on the right is very flat. It has a very large reach and a small curvature, whereas the one on the left has a small reach, large curvature, and as a result, this would be much more difficult to embed and to measure. We would need many more measurements compared to the one on the right. So let me explain why that number of measurements actually shows up in a couple of slides back. Well, let's say that we would like to cover this surface with disk of radius epsilon, and in a way end up with this kind of pepperoni pizza over here. But it turns out that the smallest number of disks that we would need to cover this surface is proportional to this expression. Now, if you imagine this as a map of UK, and each disk as a house or a state in there, then what's the smallest postal code that we would need to address all these places? Well, I've been told that you need here a kind of sequence of 6 letters, I think, to do that. And a similar story here. You know, when you have this many disks and you want to identify them, you would need at least log of that covering number measurements to be able to tell them apart. Now, in a very simplified language, the idea is that we make sure that a generic linear map preserves the geometry of a single one of these disks with very, very high probability on the choice of the map. Then, because there are finitely many of them, still that will be true for all of them. So a generic map will preserve the structure of each of these guys. And then we make sure that their order doesn't change when we map them down to Rm. And that's more or less it. That's how we end up with that expression. All right, now that we do have a good measurement operator, we collect them, we put them in this vector y. We can answer plenty of questions. We can reconstruct x. We can find the location of x on the manifold, on the surface, or underlying parameters of it, in a sense. And, well, some of it were discussed in that paper that I put earlier, but there are lots of things that we can do from here. And let me talk about a couple of very specific examples here. So I'm going to talk about nonlinear time series analysis. So the idea here is that, well, you do have a time series. You assume that you model the data as a scalar measurements of a dynamical system. So let me explain with an example. Well, on the left, we have the famous butterfly trajectory of the Lorentz attractor. It starts at time 0 and kind of goes through the space R3. Then every t seconds, we take one scalar measurement from the state of the system. And by that, I mean we just compute the inner product of the current state of the system and a vector phi. It doesn't have to be linear, but just makes the presentation easier. And then we plot these measurements. You know, this gives us a time series like this. In this example, I think I took the phi just to keep the first coordinate of x. All right, now let me introduce the delay coordinate map. Starting with the time series data and an integer m, we stack every m consecutive data points into a vector. So we have the green vector, the red vector, and we keep doing this over and over. And you know, then that gives us a trajectory in Rm. I think m is 3 here. And the map from that very first trajectory to this one is called the delay coordinate map. Now, what's remarkable is that we only use the time series data to generate this trajectory. And yet it looks remarkably similar to the original one. This one. So that's important because we can answer all sorts of questions about the original dynamical system by just looking at the time series data. So it's very natural to ask whether this delay coordinate map that we just discussed, would that preserve the geometry of the original trajectory in the sense that the distance between every pair of points on that trajectory is nearly remains the same. We can stably embed that with this map. All right, to answer that question, suppose that there is a surface or manifold M that envelopes the trajectory in original space. And this is usually called the attractor in the sense that this enveloping manifold attracts the trajectory of the system from any starting point. then this delay coordinate map is indeed a geometry preserving map if this is true. The stable rank of the system, which I'll introduce, is large enough. Now the right-hand side, I have simplified this quite a bit, but this exactly matches the one from earlier where we're trying to embed the enveloping manifold itself, right? The left-hand side, this stable rank quantity, so I will not formally define it, but it ranges between 1 to m. On one hand, m is perfect. If your system, your dynamical system is predictable and well-behaved, then a stable rank is large. Let's say it's m. That means that if you just want to take measurements of the system, reliable measurements, you just crank up the number of delays. M was the number of delays in that delay coordinate mapping. And eventually this inequality will be met and everything will just go nicely. But at the other extreme, if your system is chaotic and unpredictable, then let's say stable rank would be very small, and it would be very small, and let's say it's 1. Then regardless of number of delays or however you tweak the parameters of that map, this will not be met, and you will not be able to successfully measure that system. So as a rule of thumb, the more chaotic the system is, the more difficult it is to capture it and measure it. Well, just one quick word about why do we actually need this stable rank? Why does it show up instead of just the number of measurements, m, as it was before? It turns out that if we unwrap this measurement operator, it kind of looks like applying a random block diagonal matrix with non-zero blocks that are copies of the measurement vector phi to a vector that just contains the states of the system. And whereas before we had this full m by n Gaussian or matrix, for example, now we have a matrix that has plenty of zeros, so it's much less random. And the price that we end up paying for this reduced degree of randomness in our system is that having a stable rank, which is a weaker thing than just having m itself. All right, so last example here is I want to talk a little bit about the streaming PCA. Well, principal component analysis, if you have some data, it finds the best subspace that fits the data by minimizing the sum of distances to data points. Now, if you have generally you have high dimensional and large data sets. So a very important question is what you would do if you wanna, if there's a stream of data is coming in, and you want to compute the PCA of those data points, and you have some missing integers in them too. So more specifically, suppose that there is an r-dimensional subspace S in Rn, and there is a stream of generic vectors drawn from this subspace, let's say S1, S2, and so on. Now, either accidentally or deliberately, these vectors undergo erasure or subsampling. And you end up with these measurement vectors y1, y2, and so on, where the dark integers are missing. So now the question is to come up with a streaming algorithm that would estimate the original subspace S. And by streaming, I mean that at any time, you're only allowed to store very little of the data. And that's important when you have high dimensional data and a lot of it. OK, so here's what we're going to do. We're going to take a block size B, which is larger than the dimension of that subspace. And we're going to partition the data into consecutive blocks of size B. So we have all these very thin blocks stacked. Now I'm going to set to 0 everything that I haven't observed, so all the missing integers. Then I'm going to apply cheap PCAs to each of these blocks and find the best subspace that fits each of these blocks. And I will call them y1, this is script y1, and y2, and so on. Now these subspaces are random because the missing inter is random. And they all belong to Grassmannian G, N, and R, the manifold of all subspaces, of all R-dimensional subspaces. So it's very natural to ask, okay, if I have these random subspaces, would the average of them be close to the original subspace? Because ideally, if there are no missing integers, each of them would span the true subspace, and we are done. So maybe if you have some missing integers, that would still be to some extent true. Well, first of all, what does it mean to take expectation, to take average on a manifold? And if you have a bunch of numbers, xk's, then it's very easy to compute the average. But also, the average minimizes the sum of square distances to all the data points. So on a manifold, let's say on the Grassmannian, we can use the same idea. All we need is a metric. Let's say I'm going to use the canonical metric, where the distance between subspaces A and B is norm of the difference of the projection operators onto those subspaces, which is just normalized or something. Now, given a metric, we can define the average of these subspaces, for example, YKs from the last slide. And we will just define the average subspace as the one that minimizes distances to all those sequence. And this is, by the way, usually called the Frechet mean on the manifold. Now, the question is that, well, if you were able to compute this average, how far would it be from the true subspace? What is the bias of this estimator? It turns out that, now here is an assumption that I should have introduced earlier, but we assume that the missing integers of the incoming measurements are random. So with a probability of p, you keep an integer, and otherwise with probability or 1 minus p is discarded and missing. Then if you go through this process that we just described, you have this original subspace, you generate these blocks and their subspaces that fit them. You take their expectation, then their distance, the bias of this operator would be bounded like this. Well, if you increase n, this bias drops, reduces. If you increase p, if you keep more and more samples, then naturally this right-hand size also reduces. Ideally, if p is 1, then these two are equal. Left-hand side is 0. This polylog n is just a small logarithmic term that depends on n. And this nu of s is some sort of coherence of the subspace. It turns out that some subspaces are more difficult to estimate, especially those that have their energy concentrated in a few of their rows. This last term, maybe I can explain a little bit more, but this shows up because effectively what you are doing is covariance estimation with noise. It just happens that noise is in terms of missing integers here. So this is to be expected. And it suggests that the blocks should be almost a squarish in their size. And just in passing, I should say that, well, it's not very hard to compute this average. Just the same way that you can compute the average of a bunch of numbers with, say, a running average, just updating it with every number that comes in. You can do the same for subspaces, this time on the Grassmannian. Suppose your current estimate is S hat k minus 1. Then the new subspace comes in, yk, with the new block of information. You just move along the path that connects the 2 points on the Grassmannian, which is, by the way, usually called geodesic. And there is a closed form for points along this curve. Well, in fact, on the basis of that, you can furthermore improve on it and get an algorithm that we call SNIPE, subspace navigation by interpolating partial integers, which happens to be named by Baird as well, and obviously work backwards, or as my advisor would call it, acronym-driven research. Then this algorithm, the SNIPE box, converges exponentially fast to true subspace in the metric that I described earlier. That was the error metric, and have very strong guarantees for it that I probably would get time to enough explain. And actually, it turns out that as I finished early, that's sort of a miracle. So, well, thank you very much for your patience, and thank you.